Hey, I'm Luke, and welcome to Conquering the JavaScript interview. We're going to continue this series with a classic algorithm for the Fibonacci sequence. This was one of those questions where I tell my students, even if you don't quite get the recursive answer behind this solution I'm about to show y'all, just be prepared to memorize and regurgitate it and try and walk yourself and your interviewer through it. There's going to be, as always, there's different ways to solve this one. We're going to be taking a new approach in this series where I've typically done things iteratively, meaning I always use loops of some kind. We're actually going to be doing loops with, well, extra steps. We're going to be covering how functions can call functions from within themselves, right? So this Fibonacci Finder function is going to call itself from within itself, and that is called a recursion. And a big asterisk exclamation point note about recursion, if you will, is that you always need to remember to think, what is my exit condition? I need to have some kind of condition that will stop this function from continuing to run over and over and over again. Because if it's calling itself within itself, it's going to continue to do so until, like in a browser, it'll exceed its maximum call stack size and error out. We don't want that to happen. We always have to think, if I'm going to be using a recursive answer, I have to have an exit condition prepared to go that makes sense. And we're going to talk about that as we code this out. The amount of code for this one is actually going to be very, very short with this recursive style solution. And yeah, so I guess without too much further ado, let's go ahead and start conquering this one here. For an example, for those of you that don't know what the Fibonacci sequence is, you'll see it across tons of memes and things like that online. A lot of the times you'll see memes online with this swirl around over someone's image that otherwise is kind of goofy, saying, "Oh no, it's the golden ratio, it's the perfect thing." But ultimately, in mathematics, the Fibonacci numbers, commonly denoted as f lowercase function n, form a sequence, Fibonacci sequence, in which each number is the sum of the two preceding ones. Sometimes it starts at 0, sometimes it starts at 1, but ultimately that's all it is. It's a sequence of numbers where the two previous numbers added together make the next number in the sequence. Let's see if we can see an example here. Yeah, so it starts 0, 1, 1, 2, 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, and et cetera, et cetera, et cetera, and so on and so forth, right? So taking a look at how they generated the number 2, we take 1 and 1, add them together to get 2, then we take 1 and 2, add them together to get 3, add 2 and 3 together to get 5, and so on and so forth. That is the whole thing about the Fibonacci sequence, and basically we can look for a number n position in this sequence, and we could figure out what that number should be with this function, and that's what it's going to be going for here. So this is what's so cool about it. When we make squares with those widths of these numbers, it makes this kind of perfect spiral here that will continue on and on and on. You'll find it in nature. You'll find it in internet memes mostly. And that's what it's for there. That's what it's here. Like, it follows a set of rules, and it's a sequence that we can generate, which means that we can find a number at a certain position, which is where we go back to my VS Code editor, because that's what we're doing here. We are writing a function. I called it Fibonacci Finder. You might just call it ffib, whatever you want to call it. Doesn't really matter. That's going to take a number argument n, and that number argument n is going to represent a position in the sequence, right? So the number value is what this function needs to return at that position. Meaning, if I put in an n of 7, the output should be 13. Let's go see how we get that. We're going to assume this thing's going to start at 1 rather than at 0. So currently 0 plus 1 is, well, 1. So that's where we start there. We're going to get that's the next number. Then 1 plus 1 gets us 2. And then 1 plus 2 gets us 3. I should have written this out beforehand. Then we get 5. 5 plus 3 is 8. And then 5, 8 gets us 13. And that's where that 7th number in the sequence is going to come from. Basically, we plug in what position we're looking for, an index value, if you will, if this is an array for us coders, which is what we are because you're watching this video. That was dumb, Luke. For us coders, that's who we are. Like, I don't think there's gonna be non-coders watching this video. If you are, look in the description below for for a link to our full stack course if you're looking into getting to learn how to code. Yeah. So, and also like, comment, and subscribe. Everybody do that. Like I said, we put in the position of the number we're looking for, and the function should return the value of the number at that position in the sequence. So, all right, enough without further ado about Fibonacci sequence. Let's go ahead and actually begin writing some code here. Like I said before, we have to always think of an exit condition when talking about, when talking about recursion. So for now, we simply need to say if n is less than 2, I need you to simply return n because we are at the end of our recursive process here. And what this means is like if the n position is less than the second position, then we don't need to continue running our recursion and we can just return what n happens to be to stop this thing from continuing any further, right? So that's what we're looking at here. Like we're going to basically start at the end with whatever our position is, and we're going to do some crazy math to reverse engineer our way back in this sequence to get to where we want to go, right? And that's what this is going to generate here. So what we're going to say is return Fibonacci Finder plus Fibonacci Finder, okay? So what we need to do is we need to tell it that we're looking for the previous position and the one before that. And that right there, folks, is honestly all the code that we're going to need to solve this one. And like I said, recursion can be kind of mind-bending. But basically, if we kind of look at what these things represent, it's the more important part, right? So basically, we are looking at the previous and the previous position. So like if I was looking for the 8th value, we would look for the 3 and the 5, right? And minus 1 would be the current position. Let's say, okay, let's go 13, the 7th position. The previous position should be an 8, so we got to find out what that is. And the previous one before that is the 5. And those two add together is what gets us 13. So basically, that's what I meant by this thing is going to basically reverse itself all the way back to the beginning of the sequence and then add it all itself back together to get that value. And that's what this recursive process is going to do. Every single time we call it, it's going to call itself twice, which means it's going to build up that call stack fairly quickly. So that's really all there is to it. So we're going to run a console log around our Fibonacci Finder function. And like I said, we're going to plug in the 7th number, and let's go ahead and run that console log, y'all, and there we go. We got that lovely 13 up there above my fat head. That is the correct value at position 7. We can test this by going to position 6, which we know is an 8, and a 5, and so on and so forth, right? So if I wanted to know what the 25th position was, that is a fairly large number. We can also probably go confirm that online here. So 25th number of the Fibonacci sequence is indeed 75,025. For some fun stuff here, let's go ahead and add a console log. That's going to say function called, so we can see how many times this sucker ends up getting called, because now I'm actually kind of curious myself. And like I said, it's spamming me. Look how many times. I mean, it's going like gangbusters to generate this this value here. It is still logging, and yeah, so as you can see, this recursive process got gnarly fast. I mean, I probably shouldn't have done it at a value this high. Oh boy. All right. Let's try that again. Hold on, folks. Let's instead, I would like to call it not at the 13th position, but at the 7th position, so we don't have so many console logs. I realize the 25th position is going to have a lot of recursion going on. So it ended up spamming my terminal so much with function called console logs, it ended up locking the terminal there momentarily. But let's try it again with a less ridiculous call right there. And as we can see, to generate, that's odd how it, why did I put 233? That shouldn't be the case. What did we manage to break here, y'all? By simply adding a console log? Hold on. That seems odd. Oh, I didn't save the file, did I? I think that's what I ended up doing. My bad. Yeah, okay. I didn't save the file, so we were looking at an old output. So now I'll have the correct output finally, which is position 7, console logs, and it should spit out 13 like we expected before. There it is. And if I save the file now with my function called console log, we can see that the recursive process called it quite a number of times in between right there to get that 13, right? So that's what's happening right there. We can maybe even do like a counter. Counter plus plus every time this thing is called. And then after that is all said and done, we can then console log our counter. And it got called 41 times for figuring out the 7th position because it had to call that many. Yeah, that's pretty gnarly there, folks, to look at how many times this function called console log is appearing right there. But yeah, that's your solution to Fibonacci. I know I kind of went off the rails there by trying to like log the amount of times this thing is called and then visualizing how many times it's called and whatnot. But ultimately, this is the code you just need to kind of memorize to pass. If you get asked this question in an interview, which I've had students get asked, to pass it no problem. And being able to, even if you can't define the recursion process specifically, being able to step by step walk your interviewer through what these positionally represent in order for it to kind of like reverse engineer the whole sequence to generate that number, right? Another solution would be to just pre-compute this by writing out an array of the entire sequence and then just finding its corresponding index position of what will be n plus 1. Oh, n minus, it would be like n plus 1 since it starts counting at zeros. So yeah, that'd be the goofy solution that you might also write, saying, hey, what's this sequence here? Let's go back to where I had that console log. Like, I would laugh if y'all do this. Let me know. Going to your interview and writing out like an array with the values ready to go. And when they ask you to run this function, I would say, yeah, just add n plus 1 to get, boom, that position right there. Or actually, no, n minus 1 since it starts counting at 0. I don't know why I kept saying plus 1, right? So yeah, then you could just pull the number directly from the array and call it a day. Pre-computed, that's the most optimal solution, but more of a meme answer. And again, read the room. If you find that they could take a joke like that and laugh about it, then go for it. Otherwise, don't do it. But yeah, okay, enough rambling at the end of this video. Make sure to like, comment, subscribe, get involved in our community, check out the description links below, and we're going to keep on conquering this interview process by tackling one algorithm and data structure at a time until, well, I run out of ideas. So that's all for now.